Welcome to the Deep Dive. Today, we're really getting into something that might just change how you think about the way intelligence builds up inside large language models.
That's right. We're looking at this paper, Rethinking Reflection in Pre-training.
And it seems to challenge some common assumptions, right? Especially for those of us studying ML and AI.
Exactly. The usual story, is that this ability to reflect, to look back at its reasoning, find mistakes, fix them, that really comes later, maybe in post-training with RLHF and things like that.
But this paper argues differently.
It argues very differently. The researchers from Essential AI, they're showing evidence that reflection doesn't just pop up later. It actually starts and gets better during pre-training.
Okay, hold on. So for someone learning this stuff, what's the big headline? What's the core finding here?
The core finding is that this critical skill, reflection, isn't just a result of fine-tuning. It emerges and improves significantly just through the massive scale pre-training process itself. That's a pretty fundamental shift.
So pre-training isn't just about soaking up data like a sponge. It's also about learning how to think, or at least how to check its own thinking.
That seems to be the implication, yeah. And the way they studied this is, frankly, quite clever.
How did they do it? How do you even measure reflection inside a model?
Well, they use chains of thought. Those step-by-step reasoning paths models sometimes output.
Right, the co-feeds.
Exactly. But here's the twist. They deliberately mess them up. They put errors into those chains of thought, creating what they call adversarial examples.
Okay. Like planting a mistake in a math problem's solution.
Precisely. And then they checked if models at different points in their pre-training could actually spot and fix these errors. It's a controlled way to see if that reflective capability is there.
That makes sense. A direct test. And they looked at different kinds of reflection.
Yeah, two main types. First is self-reflection. That's the model looking back at its own reasoning, kind of like proofreading your own essay or debugging your code. The second is situational reflection. This is where the model evaluates a reasoning chain that came from somewhere else, like one of those deliberately flawed cotees they created.
So spotting your own mistake versus spotting a mistake in someone else's work.
You got it. And to make sure this wasn't just, a one-off effect for a specific task, they built 6 different data sets.
6? Wow. Covering what?
A real range.
Yep.
Mathematics, coding, logical reasoning, even knowledge acquisition tasks. They wanted to show this wasn't just a quirk of, say, math problems.
Right. Showing breadth. So our mission today is basically to unpack this research, understand what it means that reflection starts so early, and figure out the implications for students like you listening who are building expertise in ML and AI.
Exactly. Let's dive into the evidence. Figure 1 in the paper seems like a good starting point. It looks at OLMO 2 performance on tricky word problems.
Yeah, GSM-8K Platinum, these adversarial word problems. What's the key thing there?
The key thing, especially for folks thinking about training models, is the trend. As the pre-training compute, basically how much training the OLMO 2 models got increased, their accuracy on these difficult problems also went up.
Okay, bigger training, better performance. That's expected, maybe?
Well, yes, but the paper links this improvement specifically to the models getting better at reflection. It's not just being bigger, it's about developing this ability to catch errors, which gets better with more pre-training compute.
Ah, I see. That's why they get better. That's interesting. And figure 2 gives a specific example, right? That coding task.
Yeah, figure 2 is a great illustration. It shows a partially trained OLMO 2 model, 32 billion parameters, I think. It first messes up a coding problem. It gives the wrong input for a function. But then the researchers prompt it with its own mistake, followed by just the word wait, just that. And the model corrects itself. It provides the right input.
Just wait. What? That's all it took.
Apparently. It suggests that simple prompt tapped into some nascent self-correction ability that was already developing. For someone building these things, that's pretty relevant, right? Even small cues can trigger this internal review.
It's like jogging its memory, or maybe prompting that internal hang on a sec moment.
Sort of, yeah. And it's not just anecdotes. The numbers back this up quite broadly.
What did the quantitative results show?
Across their 6 data sets and all the different OLMO 2 checkpoints they evaluated, they saw situational reflection spotting errors and external reasoning in, get this, 231 out of 240 cases.
Wow, that's almost universal.
It's widespread, definitely. And self-reflection, spotting its own errors, showed up in 154 out of 240 cases. still very significant. It really suggests reflection isn't some rare thing. It's becoming baked in during pre-training.
And they even quantified the link to compute, right? That Pearson correlation.
Yeah, a positive average correlation of 0.76 between accuracy and the log of pre-training compute.
So translate that for us. What does 0.76 mean practically?
It means there's a strong positive relationship. More pre-training compute tends to lead to better reflection and thus better accuracy on these tasks. If you're thinking about resource investment, this suggests putting more into pre-training pays off in terms of reasoning quality.
Okay, that makes sense. Now they talk about explicit versus implicit reflection. Can you break those down?
Sure. Explicit reflection is when the model actually, says it found a mistake. It uses specific words. Table 5 has examples like, wait, 42.stats is not a whole number, or even, wait, we forgot the cow. It's verbalizing the error it found.
It's showing its work, including the part where it realizes something's wrong.
Exactly. Implicit reflection is different. The model still corrects the error, gets the right answer eventually, but it doesn't explicitly state what the mistake was or that it made one. It just silently fixes its internal path.
Like quietly correcting course without announcing it. How did they tell the difference automatically?
They used another LLM, DeepSeek v3, trained specifically to spot those explicit reflection phrases in the output. They checked its accuracy against humans and found it was pretty good high precision, meaning when it said explicit reflection, it was usually right, even if it might have missed some cases.
Okay, so they had a way to measure this. What did they find when comparing explicit and implicit reflection as pre-training increased?
Table 6 is key here. For most tasks, as pre-training compute went up, two things increased together: overall accuracy and the rate of explicit reflection.
Ah, interesting. What about implicit?
Implicit reflection didn't show that same strong upward trend. It suggests that with more training, models don't just get better at fixing errors, they get better at articulating the fact that they found an error. They rely more on that explicit mechanism.
That is fascinating. It sounds almost like developing self-awareness about the reasoning process itself.
You could maybe interpret it that way, yeah. It's becoming more aware of its own steps.
Which leads nicely into the experiments with those trigger phrases, like just wait, what was the deal there?
Right. Figure 4 shows this on the GSM 8K Platinum math problems. They compared performance in 3 scenarios. No trigger at all, just the wait, trigger, and a very direct trigger, like, wait, I made a mistake.
And what happened? Did models improve even without a trigger?
Yes, definitely. Performance improved with pre-training even with no trigger, which points back to that baseline implicit and maybe some explicit reflection developing naturally.
But the trigger helped.
Significantly. Just adding wait gave a noticeable boost in accuracy. And the thinking is that this simple word was enough to elicit more of that explicit reflection we just talked about.
And how did wait compare to the wait, I made a mistake trigger?
It landed in the middle. Performance with wait was better than no trigger, but not quite as good as when the model was explicitly told it made a mistake.
So wait acts like a nudge. It prompts the model to use its reflective ability, but the model still has to figure out if and where the mistake is.
That seems to be the idea. The paper suggests the effectiveness of wait depends on how much explicit reflection capability the model has already built up during pre-training. It's like the prompt leverages an existing skill.
Makes sense. Now, the paper also mentions that self-reflection checking its own work is harder than situational reflection. Why is that expected?
Well, think about how they test it. Self-reflection is measured on questions the model already got wrong on its first try. So the starting point is failure. It's just inherently tougher to spot flaws in your own reasoning, isn't it?
Absolutely. We've all been there. Easier to critique others.
Exactly. Table 7 shows this quantitatively self-reflection is rarer. But Figure 5 shows something hopeful.
What's that?
Even though getting the final answer right after self-reflection might lag a bit, models do get better at explicitly identifying their own errors as pre-training increases. They get better at saying, oops, my logic here is wrong, even if fixing it perfectly is still developing.
So, the awareness of internal errors improves, even if the correction isn't perfect yet.
Precisely. It shows a progression. And this leads the researchers to speculate about something quite interesting, a potential critical threshold.
A critical threshold for pre-trained self-reflection. What would that mean?
They hypothesize that maybe once self-reflection ability reaches a certain point during pre-training, it could unlock much more sophisticated reasoning capabilities later on, especially when combined with post-training methods.
So focusing on boosting this pre-trained self-reflection could be a pathway to, well, smarter AI.
That's the potential implication, yeah. It points towards a promising direction for future research.
This all seems to tie into practical concerns too, like compute costs. They discuss a train time versus test time trade-off.
Yes, Figure 6 illustrates this quite nicely for the OLMO232B model. Basically, it shows that if you invest more compute during pre-training,
Right.
you might need less compute at test time to reach the same accuracy level. Specifically, you might need fewer rounds of using that weight trigger to coax the model into correcting itself on hard problems like GSM-8K Platinum.
So more upfront investment in training builds a more inherently capable model that needs less hand-holding or intervention later.
That's the idea. Building that strong reflective foundation during pre-training could lead to more efficient inference, which is, a big deal in practice. It affects deployment costs, latency.
Big implications for resource allocation, definitely. And this isn't just about the OLMO models they focused on.
Doesn't seem like it. Figure 7 looks at a different model family, Quen 2.5, and they saw a similar pattern. Bigger models in that family, representing more pre-training scale, also performed better on these adversarial reflection-requiring tasks.
So it suggests this might be a more general principle of how LLMs learn.
It points that way, yes. That the emergence of reflection during pre-training isn't just an artifact of one specific architecture or data set.
Okay, let's pull this together. For the MLAI students listening, what are the really key implications here? What should they take away from this deep dive?
I think one huge takeaway is challenging that old idea that sophisticated reasoning only comes from post-training or RLHF. This paper strongly suggests the foundations, the ability to reflect and self-correct, are laid much earlier during pre-training.
So understanding pre-training becomes even more critical, not just the data, but the capabilities being built.
Absolutely. And you want to build robust, reliable models. Understanding how reflection emerges during that phase is crucial. It could totally change how we design pre-training objectives or curate data sets in the future.
Trying to explicitly foster this reflective ability from the start.
Maybe, yeah. Instead of just hoping it emerges, perhaps we can design training to encourage it more directly. This could lead to models that are intrinsically more self-aware and less prone to certain kinds of errors.
And it connects to the ongoing discussions about scaling laws and compute.
Right. Definitely. This train time versus test time trade-off is a big part of that. Knowing when and how reflection develops helps make smarter decisions about where to put those expensive compute resources. Do you push pre-training further or rely more on inference time strategies? This research gives us more data points for that.
Are there still big open questions left by this work? Where does research go next?
Oh, for sure. A big one is, how exactly does this pre-trained reflection interact with post-training? Does fine-tuning amplify it? Does RLHF build on it specifically? We don't fully know.
And identifying what in the pre-training data actually drives this.
Exactly. Is it seeing examples of reasoning? Is it certain types of text structures? Understanding the data drivers could be key to intentionally boosting reflection. Lots of interesting paths forward.
So wrapping up, the main message seems to be, reflection starts early. It's not an afterthought. It's part of the foundation built during pre-training.
That's the core of it. This ability for models to critique themselves, it's developing surprisingly early in their life cycle.
And for everyone listening, for the future researchers and practitioners understanding these deeper mechanisms, how models learn to reason and self-correct, that's going to be absolutely vital for building the truly reliable and capable AI systems we're all aiming for.
Right. So maybe a final thought to leave people with. How might these insights change your approach? If you were designing a pre-training run tomorrow, knowing this, what kind of data or objectives might you consider to specifically enhance this nascent ability for self-reflection and error correction?
Something to definitely chew on. Thanks for breaking that down for us.
My pleasure. It's fascinating work.